Welcome to NASA Edge.
An inside and outside look at all things NASA.
Hey, we're joined by Steve Gaddis, who's the program manager for the Game Changing Development Program Office and our special co-host. How you doing, Steve?
Doing great. Glad to be here.
Now, last time we had Steve on the show, we were talking about nanotechnology, which was pretty cool.
Very cool.
What are we going to talk about today?
Robots.
Awesome.
We love them, don't we?
We really do love them. Tell us exactly what robots you have in the game-changing portfolio.
So you're probably most familiar with R2, humanoid robot that we've got on station. R5 is the next generation. Have you seen R5?
Yes.
Yeah, it looks like Iron Man to me. But
Yeah,
Iron Man,
it really does.
You better believe it. That's what we were hoping for. We've also got a robotic arm, and it's being developed at Langley. It's one of those long-reach arms, so if you get close to an asteroid, it can reach out and take a piece of it off or attach and bring the vehicle to it.
All right.
A lot of this work is being done at Johnson, some's being done at Ames. Speaking of Ames, have you heard of Astronomy?
No.
What about spheres?
Hey,
Yes.
we did a segment on spheres a couple years
That's
ago.
right, you did. And so Astronomy is the next generation of spheres. It's like spheres on steroids. It's going to do a lot of cool things to help the astronauts on the inside of station, and we're hoping it can do some observation on the outside of station. One moment, please.
Hey, it seems like that. It sounds like you have a lot of different robotic vehicles within your portfolio, not from humanoids to just regular robots.
Absolutely. We're covering robots that are humanoid in fashion. We're covering robots that operate spacecraft. We're covering robots that are a rover,
right.
a robotic rover. We're something like even a vehicle, if you will. Thank you, B.
And I understand that you have another robotic vehicle called Resource Prospector.
Absolutely. RP is going to be going to the moon,
right.
And we're developing the rover. We're partnered with HEO for that activity. It's going to take samples, it's going to gather data. It's been a long time since we've been on the surface of the moon. It's very exciting.
Well, the cool thing is, and thank you for giving us the opportunity, Franco and I had a chance to go down to Johnson Space Center and actually see those robotic vehicles in action.
Yes, sir.
And what we're going to do is we're going to start up with the first one, which is the Resource Prospector. I had a chance to talk with Bill Bluthman, who's the project manager for RP. Hey, Bill, we're inside Building 9 at Johnson Space Center, and there's a lot of activity going on this morning. I see a lot of parts, a lot of different robotic parts, which leads to human robotic systems. What's that all about?
Well, so in human robotic systems, really our goal is to really build robots that help humans explore. And that can mean a lot of different things. It can be the kind of robots that do missions before astronauts that enable future exploration. It can be working shoulder to shoulder with astronauts during a mission, and it can be really cleaning up after. So it has a very broad set of areas where we can apply this work, but the ultimate goal is to really make human exploration more effective.
Well, I understand you have a number of activities within HRS. What do you have?
Well, right now we've got rover technologies, where we're building a small rover to explore the poles of the moon.
I think that's it right now.
Yeah,
Yes.
we're testing about 20 feet from us. We're testing the suspension. The ultimate goal of that machine or that mission is to really look for water. We've had recent missions, orbital missions and impact missions that have shown that there's in fact water at the poles of the moon. And the goal of this mission is really to touch it, process it, understand just how much it is horizontally across the surface, as well as what it looks like subsurface.
So what you're basically doing there for the Resource Prospector, you're taking the data from, let's say, LCROSS and LADEE and those previous science missions. Now you're going to apply them.
Yeah, it's just kind of the next step in really getting at the water that's on the pole. This is an interesting project where, within Game Changing, we're partnered with the AES Advanced Exploration Systems program, where the rover team is really developing the technology. And we've built a prototype this year, and once we've developed the technology, we'll hand that work over to AES to really do the flight work.
Now, is it going to be that loud once it's on the lunar surface?
Well, no, in the moon it will be very quiet.
That's true.
Without an atmosphere, those sounds will be vibrations in the rover, but you won't be able to hear it audibly.
And after we spoke with Bill, we had a chance to take the RP out to the rock yard, and we talked to design engineer Mason Marquis. So Mason, looks like we have a new rover in the works, the Resource Prospector.
Yeah, that's right.
What's it all about?
Yeah, we call this the RP rover. So this is basically a prototype of a robot we want to send up to the moon to go to the north or south pole of the moon. We want it to drive around on the moon's surface and then go down into craters that haven't seen light in 1 billion years. And once we're in those craters, we want to look around, find an interesting spot where we might think there's some organic compounds, and drill down, take a soil sample, bring that up into the robot, process that soil sample, and then see if we can make a few drops of water from all that. If you can make water when you're on the moon, that proves a lot to us. I mean, that means you don't have to bring everything next time you go to the moon. You don't have to bring your water, and if you have hydrogen, you can make fuel there as well, which would be incredible.
Now, what is your role in with the Resource Prospector?
So I was one of the engineers working on the rover side of it. This is a multifaceted project where we've got engineers at Ames, we've got engineers at JSC, KSC, and I worked on the rover side of it, so I was doing the chassis design, basically making sure that everything's solid on there, holding all the wheel modules together, integrating all of the payload components onto heat spreaders. We've got a radiator on top and a solar panel on the back, which are mock-ups right now, but that was all part of the chassis structure that we put together.
Now, NASA's built a lot of rovers in its days, and looking at the size of it, what's the size comparison to the other rovers in the past?
Yeah, so this falls right in between the Spirit and Opportunity rovers and the Curiosity. So it's kind of fits that blend right between them. It's not the biggest rover we've ever made. Right. It's definitely not the smallest.
And what are some of the differences from the engineering side looking at the chassis?
Yeah, so a lot of the rovers you see out there have 6 wheels. And they're a different setup because those front and back wheels can move in any direction. They've got 4-wheel steering, but the middle wheels kind of stay stagnant. They don't do any kind of steering. On this vehicle, we have 4 wheels, but all 4 of them can rotate 360 degrees.
Oh, okay.
So we can make this vehicle drive completely sideways, and we kind of took that from a lesson learned with the Spirit and Opportunity rovers where they were getting stuck in sand and in some tight spots, and they were always able to get out. They're really capable robots, so we thought we could do a little bit more by having each one of the tires be able to spin.
You've been around for about a year now with this project?
Yeah, that's right.
What are some of the challenges that you faced so far?
Yeah, so one of the big ones was trying to build a robot that worked here on Earth so that we could do our performance testing here, but fit the size bill that we wanted to go on a rocket to be able to get to the moon. So this robot represents the size of the real rover that we want to send to the moon. Of course, the weight of it isn't quite accurate. We couldn't build this 6 times lighter so that the forces on the wheels were the same. So we had to make this strong enough to stand up in Earth gravity, but only fit in the size to go to the moon. But we also wanted to tackle a lot of the aspects that you need to go to the moon. So working in a vacuum, working in extreme temperature differential, so it's really hot in the sun, really cold in the shadows. So we started tackling some of those technologies and laying this out so that the thermal properties of this robot are very similar to the one that we want to send to the moon eventually.
I mean, are you going to actually be able to test this rover in a 1/3 G environment like the moon?
So ultimately, we want to put this on Argos, which is our gravity offload machine. So right now we have the parts coming out of the shop to mount this up to there. So we're going to see how this rover performs when it doesn't have all the gravity on it, which for us, with Terra mechanics, how it moves through soil is really important. Because out here, we're not quite getting accurate testing because the wheel is sinking down in the ground more than it ever would on the moon because of that weight difference.
So I noticed on the front half of the rover, we have the science instruments sticking out from the top there?
Yeah, we have actually 2 structures popping up there. We have the drill, which is made by Honeybee Robotics, and that's what we actually go down and take that soil sample with. And then we have a mast, and that mast can retract. It stows in a down position, which is how it would be for launch. It releases, goes to an upright position, locks in. And on top of that mast, we have cameras and lighting, and there's going to be an associated kind of 3D mapping structured lighting on that. So that's on a pan-tilt unit, and then on top of that, we have the comm dish, which is on a pan-tilt unit, which we use to talk back to Earth.
Now, is the idea behind this rover very similar to, say, Curiosity and Spirit and Opportunity, where you're going to be sending it a set of commands for it to perform each day on the moon?
Yeah, absolutely. What's different about this, though, is it's only going to be a 6-day mission on the moon.
Oh, wow.
Yeah, so we're not going to be able to have the energy sources. It's going to get too cold. We're going to lose the sun. So there's a very small window of time that we can go up to the North and South Pole. So we're going to be power packing as much into those 6 days as possible.
Now, I do have one question. I didn't see a pickaxe on the rover. I mean, did you forget that on purpose, or do you think you're going to put a pickaxe on there?
No, we don't need a pickaxe.
The only reason why I'm asking that is because Yukon Cornelius, who's the greatest prospector in all the land, that's how he got his gold. So I'm wondering, it looks like it has some gold color to it.
Yeah.
It's a prospector mission. You think it would have a pickaxe?
Maybe I'll take that back to the board, as a lesson learned or something. Yeah, need more weaponry.
That's a good call.
Yeah.
One of the great things about covering these missions is looking at the size of these rovers and the technology. I mean, this rover, as Mason was saying, is in between Spirit and Opportunity and Curiosity.
Yeah, it's a little bigger than the size of this table.
I think one of the interesting things about the mission is that it's going to be mining for water in the polar regions.
That's what's game-changing about the mission.
High risk, high reward.
And you talk about risk-reward. This guy has to be the fastest mission that I think I've ever seen out of NASA, that it's not going to actually operate that long on the lunar surface.
Absolutely, Franklin. You hit a hot topic. We're trying to do it as cheaply and as fast and safely as we can.
And get all the data that you need.
And get the data that we need. Speaking of high risk, high reward, remember we were talking about R2?
That's right.
Well, B recently had an opportunity to go learn more about R2.
B?
B.
Okay.
Vinny, the last time I saw R2, it was only a torso, and it was in a lab in another building here at Johnson Space Center. Can you tell us where R2 is now? I mean, obviously you've made some improvements.
So, since the last time you were here, we've sent an upper torso up to space station in order to start learning how to help astronauts perform tasks side by side. That was just an upper torso and was fixed to a stanchion. So he could not move, could not be mobile. So we sent up a pair of legs a couple years ago, had them installed, and now he's mobile.
And literally walking around station or grabbing?
Not yet. We are currently working on teaching him how to look for handrails, avoid obstacles, and that's exactly what we're doing here today. In this mock-up, we have some of the walls modeled from space station, as you can see here, and then handrails just littered across this mock-up because that's exactly how it looks on station.
That brings up an interesting challenge. You're down here on the ground developing things for R2, and then you actually have to figure out how to teach R2 up on station to do that. How does that happen?
So what's great is that we have an internet connection to station, albeit a very slow internet connection, but we can push up software updates to the robot. So as we do development here on the ground and we polish off a new feature or tool, we can just send that up to the robot after it's been safety tested, and Robonaut on station has a new capability.
Now, do you have to work with the astronauts on something like the legs, which seems to me he can't just put them on himself? You know, do you have to work with them in conjunction with astronauts so they can help Robonaut with some of the new hardware additions?
So, like a lot of tasks on station, we have to go through training with astronauts and basically teach them how to perform surgery on a robot.
Exciting.
Yeah, that's, you get to play doctor for a day because you get to open up Robonaut, open up all of his covers, and literally dive into his innards in order to make some of those hardware connections and add or replace hardware.
Vinny, in looking at the setup of the ISS here, you're obviously trying to simulate that environment. How do you simulate reduced gravity?
That's actually a great question. This mock-up is the ISS, but if you look at this gimbal that R2 is attached to, it's actually attached to another robot. So we have a robot inside of a robot, and this robot is called Argos. It's a gravity offloader system, and what it does is it accounts for gravity in the Z direction. So we can at least remove that part of gravity and allow him to operate in a higher fidelity environment, close to what you would see on ISS.
Now, I see you have a demo set up here. What kind of things would R2 be doing in a demo here in the lab?
So the demos that we're trying to recreate are as realistic as possible. So what we envision for Robonaut is for him to be an astronaut assistant. So one possible scenario is that an astronaut has spent all day performing tasks, performing experiments, making repairs on station, and he just could not get to something at the end of the day. So
they're great people, but they do need sleep.
They do need sleep, and they have a really hard job up there because their day is scheduled very, very strictly, and sometimes things don't always go right. So something that R2 can do is at the end of the day, while astronauts are sleeping, he can unstow out of his little cubby hole and go around and perhaps collect all the tools that the astronaut needs to perform tasks for the next day.
I want an R2 for my house. I mean, that'd be great for me.
Awesome?
That'd be great. No, that's actually awesome for the astronauts. Not only do they get the rest, but it's more efficient for the tasks that they're doing.
Yes.
Which is great. Now, I see you have the classic phaser up there. Is it on stun? Is it in safe mode? How does that work?
It's actually an RFID reader.
Okay.
We have a new system on station where we tag everything with an RFID tag, and that helps us to actually keep track of things. I don't know if you've seen pictures of how much stuff is strapped down and flying around on station, but that really helps the astronauts stay organized and locate things more quickly. So that's what that tool is used for is inventorying and finding out what is in a cubby hole before they actually open it up.
Steve, we've really made some technological advances with R2 over the years. Now we've added these
crazy legs.
Crazy legs.
That's what we like to call it.
Crazy legs.
Technical term.
And now it's operating on Argos to simulate zero-G. That stuff is mind-blowing.
It is.
I tell you what, the cool thing is that you have this robotic, humanoid robotic, R2, working with another robot, Argos. I mean, it's sort of like a robot working with the robot.
You know what's even cooler? R5. B did such a good job with interviewing R2. I sent him over there to talk with R5.
What's up with B?
Chris, I noticed that R5 looks very similar to R2, but is it more of a new replacement program or is it more of a complementary robot?
Actually, we call R5 Valkyrie. The robot's name is Valkyrie. Valkyrie is specifically intended to be a robot that works on a planetary surface, either on Earth or in the future on Mars or the Moon or some other surface. The zero-G legs that you see on Robonaut are perfectly adapted for a spaceflight environment. The legs on Valkyrie that you see are much better adapted for walking in a gravity field.
What are the challenges you have developing a robot for a gravity environment, especially since they're more human-like?
The biggest challenge going from R2 was we had to make everything lighter. So the body of R2 with the legs is in the neighborhood of 500 or 600 pounds. We were trying to get Valkyrie around 100 kilograms. We didn't quite make it that low, but right now the robot weighs in about 300 pounds and we're looking to find ways to reduce that even further. And that's primarily because we're running off a battery. So to run untethered off a battery, every pound that you're carrying around is shorter battery life. So it's like a motorcycle or anything that needs gas mileage, you want to have it be light as possible.
How are the legs being developed? I assume they have to be pretty light as well.
So if you notice, the legs on Valkyrie don't look a lot like the arms, and the legs on Robonaut do. The Valkyrie legs are specifically adapted to be a walking type environment, but they're also made to be humanoid. So we make humanoid robots to work in a human environment. So most of the world is built so humans can use it. And so it makes sense to, instead of saying, let's go back and rebuild everything so robots can use it too, why don't we just make a robot that can use the same kind of interfaces that a human can use, and you end up with a humanoid robot pretty quickly. But the legs on Valkyrie, we pulled from a number of different projects, including our exoskeleton project, to reduce the form factor and reduce them in size so that they would basically fit into those same kinds of environments the human would use.
How will creating human-like robots help us for space exploration?
So we're going to go build another infrastructure on Mars, and we build that infrastructure, we're going to build it so the astronauts can use it. My boss says, we build robots for space, but you don't send robots to a place that you want to go, and we all want to go to Mars. And so we're going to send a robot there to make things right for people and to help the people out, and to maybe participate in a caretaker role. So if we have an asset, our base on Mars, maybe it's not staffed all the time, and maybe we need somebody to take care of it while people are flying back and forth, and I think that a robot like Valkyrie would be great for that, or a Robonaut.
Now, Steve, the light on R5's chest, was that done to just rope in kids to get them interested in the technology that we have here at NASA?
Well, I can neither confirm nor deny that comment, but look at my eye, I'm winking at it. Yes, we were trying to reach that younger generation for all the right reasons, like the Avengers movie.
Right.
It's a big hit all over the world. Even my little 3-year-old grandson is all about those characters.
And speaking about the younger generation, and you talked about earlier in the show that you had these centennial challenges where university students are going to be working with R5.
Right, that is really cool. So we're developing 2 R5 units, and we're going to give those to universities to do upgrades, next generation software for walking and manipulation, and then through a solicitation, somebody is going to get one of those, and there'll be a competition called Space Robotics Challenge.
So the university students potentially could improve R5 and provide that technology back to NASA.
That's what we're hoping.
Oh, that's cool.
So Steve, you're handing over R5 to colleges and universities across the country. How about handing over the modular robotic vehicle to me?
Well, Franklin, I'm afraid that might be a long line that you'll have to get in. A lot of interested people in the MRV.
When we were at the Johnson Space Center, I had a chance to talk to Justin Ridley about the MRV, and he actually took me out on a ride.
You lost your stomach, didn't you?
Maybe. So Justin, we're here in the Modular Robotic Vehicle, or MRV. What makes this a game-changing vehicle?
Yeah, so this is an all-electric vehicle that's based on some drive-by-wire technologies. So where a typical vehicle would have mechanical linkages, this has got a electrical system. So for instance, with this steering wheel here in a normal car, there'd be a rod going down to a rack and pinion system, and that steering wheel would control the wheels of the car. Here, I've got sensors that are detecting the steering wheel angle, and there's a computer in the back that's telling these wheels which direction to turn. So this is technology that's been used in aircraft for a number of years that we're implementing into a terrestrial vehicle.
Now, you talk about computers. I'm looking at the steering wheel here, and there's a little joystick here. It feels like this is almost like an arcade game.
Yeah, in fact, the steering wheel here was modeled after some high-end video game controller systems. So just like where a video game player would be driving a race car around, he'd want to be able to feel the road. Right now, without a force feedback system in here, I wouldn't feel the road. There's no linkage between this and my wheels. So we've got a system here that adds some resistance to the wheel as I go around corners. It centers the wheel as I come out of a corner, and it gives me some feel of the road that I wouldn't otherwise have. But it is very video game-like.
Well, what about this joystick in the middle? What does this do?
Each of the wheels are completely independent in steering, so they can rotate on their own about plus or minus 180 degrees. So that gives us some control that a typical car or truck wouldn't have. This joystick allows me to yaw the vehicle while steering it around. It's kind of hard to describe, but it allows me to basically drift around corners and crab sideways, diagonal. I can drive in a bunch of different directions, and I can use this joystick to help me do that.
Man, this car is awesome. Can we take it out for a spin?
Absolutely, it's a lot of fun to drive. Let's do it.
So this car can actually do like continuously go in a circle in place?
So I've got about 180 degrees, so I can't continuously go in place, but I can drive forward and I can get basically all the way around as I'm driving forward. We call that kind of a parade mode. So when I'm in a parade and the people over there, I can tilt the vehicle over and wave to them and then tilt it back and drive away.
What's the top speed in the MRP?
So the vehicle's designed to go about 40 miles an hour. It probably can go a bit faster than that, but right now we're still learning some of the systems and we limit the speed to about 15 miles an hour.
Now, when I look at some of those smart cars, they're really kind of small, about this size, maybe even a little smaller. Those cars are made to get into those parking spots, parallel park. But you can actually just pull up to a spot and just turn your wheels and just go right into it.
That's right. We tried to make this about smart car size. It's just a little bit longer than a smart car, but if I go to a parking spot, I can just go to a specific mode in the car, take my steering wheel to about 90 degrees and drive parallel right into the spot.
Now, Justin, you just gestured to this display on the dashboard. What is that used for?
So the display here gives me a bunch of information about the vehicle. A lot of the information is something you see in a typical vehicle, such as your speedometer, an odometer giving your mileage. But then we got some additional information, such as temperatures in each of these wheel modules I mentioned before. And then because the wheel modules do rotate so much, I've got a display that shows me the direction of each of those wheels. So if I'm at my full 180-degree rotation, I can see where everything's pointed and which direction I'm going to go. I've got a few different driving modes. I select that from the panel here. I've got a regular two-wheel steer mode. We tried to develop the vehicle to feel as much like a traditional automobile as possible. So the steering wheel, the brake and gas pedal, those feel like a real car. When you're in two-wheel steer mode, hopefully you don't notice too much of a difference from a real car.
Right.
I've also got four-wheel steer mode, and that allows me to control all four of the wheels together. In that mode, I can get full 360-degree turning right on the center axis of the vehicle. So think of really maneuverable steering. Then I also have what we call omnidirectional mode. That's where the joystick comes in handy. So when I'm in omnidirectional mode, the steering wheel here, when I rotate it, it controls all four wheels together. So if I rotate to the left, all four wheels will turn to the left. Then this joystick here, this controls the yaw or direction of the vehicle. So I rotate the joystick to the left, it's going to steer the vehicle to the left. I can combine these two inputs to get some of the more kind of crazy drifting maneuvers that you see the vehicle doing.
Whoa!
Oh yeah, you might want to make sure that's
Whoa! How many hours do I have to spend in the simulator to drive this car before I can actually take it on the road?
So we did actually have a simulator to kind of develop some of this advanced maneuvering capability. I didn't spend any time in that simulator, so I just ran off the road quite a bit while I was learning how to drive it. What I described where you're controlling both the steering wheel and the joystick, that's not exactly intuitive, so it takes a little while to learn how to do that. And you want to have some area where you can kind of roll into the grass a little bit off the blacktop. But driving around there for, I don't know, an hour or so, you can kind of start getting the hang of it.
All around us there are rovers that are designed for the journey to Mars. But this vehicle doesn't look like any of those other rovers. How is this supposed to be used for future space travel and maneuverability on Mars?
Yeah, so this vehicle wouldn't be used for space travel. The vehicle was designed as a urban vehicle, like New York City, getting in and out of parking spaces and traffic. Why is NASA building a car like that? A lot of those technologies I talked about, those by-wire technologies, those are things that we want to have in our vehicles for the moon, for Mars, for things that we're going to use to explore space. We could learn a lot about those technologies by developing a car like this. For instance, all that by-wire technology I mentioned, that could create some unsafe things when you're driving down the road. When I'm driving down the road in a typical car, nothing's going to prevent the steering wheel from detaching from the wheels of the car. That's not going to happen. But here, there's a number of things that could happen. A wire could get cut, that computer could fail, a motor could die, a sensor could go bad. If any of those things happen, we have to have redundancies in place so that a backup sensor can take over, another computer can reboot, and basically control the vehicle instantaneously when any of those failures happen. You want to have the same thing on Mars. When you're driving on Mars, you got to have redundant systems as well. So that, is, in addition to some other technologies that we put in here, are things that we can draw from MRV and use for our next rovers, our robots, things like that.
I tell you what, guys, that modular robotic vehicle, that is awesome. I mean,
Awesome.
What was the riding experience like?
It was great. I actually felt like I was at an amusement park on a new ride that was going backwards and forwards, but I was actually riding in a car. And it is the type of experience that, you know, you'll never forget.
Would you drive to work every day?
Absolutely. And I would park in the smart car, the energy efficient spots. You could probably fit that in a motorcycle spot.
Now, correct me if I'm wrong, I mean, Justin said that vehicle is not designed for a Martian environment or a lunar environment. It's more designed for an urban environment. But you could use some of the technologies in that vehicle for future vehicles.
Absolutely. What our plans are to use it as a test bed, right? We'll put like a high energy battery in there. We'll put a regenerative fuel cell in there. We'll put some new steering apparatus in there, maybe some compact type linkages, and some communication and navigation.
How about a door and some airbags?
Well, if you get to drive it, we might consider that.
Yeah, well, you know, speaking of driving it, I want to drive it.
Right.
I want to, the next time we go to JSC, I want to make sure, can you make sure that I
We
get an
can make
opportunity?
sure.
I appreciate
I've got connections.
it. Yes.
Talking about what he really wants to do is he wants to put that MRV in the next Fast and Furious movie.
That would be...
Already in the works.
Wow.
Yeah.
You got that right.
Wow.
Yeah, and I'm going to be Dom's sidekick.
That would be game changing.
It would be.
All right, we got one beef with you before we wrap up the show. B. Why you call him Blair B?
What's that all about?
Blair, it's B1138. That's our newest robotic prototype.
Get out of here.
Yeah.
Seriously?
Yes.
I mean, anybody who uses Blair as a robot, that's high risk, no reward.
Well, you got me on that one.
There you go.
Yeah. Let me show you.
Activated.
What
Flawless.
in the world is going on here?
Seriously? If that's a robotic Blair, then where's the real Blair?
No cognitive response at all. Really bad AI.
Well, recycle what you can and discard the rest.
Recycle? This is all 100% usable. What do you mean? I'm not a robot. I'm a human being. I'm fully cognitive. I got an 800 on my SAT, at least one of them. I could take it again. I'm human. I'm a human being.